First of all, we all know that whenever we have a function of one variable, when y is a function of one variable, we always got a two-dimensional figure, which was very easy to observe. For example, if we had y equals to x, so we had a situation like this. It was very easy to see. Here, we have constraint optimization of a function of two variables. So z will be a function of two variables with respect to an equality constraint like this. Gxy is a constant. So here I will be having an expression in two variables. For example, x plus y equals to 3. So this is a diagram, or this is a curve or a line in 2D. And this is going to be a figure in 3D. Okay. So basically we are going to optimize a 3D figure with respect to a constraint which is lying in 2D. For example, suppose we have this thing. Optimize z equals to x square plus y square with respect to x plus y equals to 1. Suppose we have this kind of a situation. Now here, you can notice that z is nothing but a function of two variables. And this is my constraint gxy equals to c. So when I'm going to make this line in 2D, I'm going to get something like this. This is x-axis, this is y-axis, and then x is 1, y is 0, y is 1, x is 0. I'm going to get a line like this. Now, how is this figure going to look? Okay, just have a visualization. For example, if I take z equals to 1, I will be getting a circle of radius 1. If I put z equals to 2, I will be getting a circle of radius root 2. Okay, because x square plus y square equals to r square is a circle of radius r. If I put z equals to 9, I will be getting a circle of radius 3. So note that as z is increasing, I am getting bigger and bigger circles. So I am getting concentric circles. So basically what is happening is this. This is x-axis, this is y-axis, this is z-axis. So when x and y are, both equal to 0, I get z equals to 0. Then as we put z equals to 1, okay, so I am going to get a concentric circle, x square plus y square equals to 1. So basically the projection on the x-axis will be a circle of radius 1, something like this. Okay, when I take z equals to 2, the projection will be a circle of radius root 2. When I take z equals to 9, the projection will be a circle of radius 3, and so on. So basically, if we continuously put, these concentric circles one over each other with increasing radii, we are going to get something like this. We are going to get a funnel or a cone-like structure. So there is no end to it because z is increasing. So it will look like something like this. Okay. So that means when I put z equals to 1, so basically I am going to cut a concentric circle like this. When I project this into the xy plane, I get a unit circle. So you fix z equals to 1, okay? You get a unit circle on the xy plane. You fix z equals to 2. You again get a unit circle on the xy plane. So these unit circles are nothing but the level curves. So what are the level curves of this function in two variables? We are fixing the values of z and we are seeing how the function looks like if it is projected onto the x-axis or xy plane. Okay, the 2D projection. For example, if we take a football, okay, and if we look at a 2D projection, so we would definitely be making a circle. Okay, so a circle is a 2D projection of a football or a sphere. So similarly, what is happening? To draw this diagram, we just observed how the level curves were looking like. And now what you do, you mount these concentric circles with increasing radii one over the other, and you will get a funnel-like structure. So that is a geometric way of seeing how the figure will be made. Okay. Now, let's see what is happening now. Now you have this kind of a situation. This is x-axis, this is y-axis, this is z-axis. So we are making a rough figure, and we know that z is positive because z is equal to x square plus y square. Suppose something like this is happening. Okay. Now we know that we have the constraint x plus y equals to 1 lying on the 2D plane. Okay. So we have a point 1 comma 0 here. We have a point 0 comma 1 here. Okay. Now look at this point 1 comma 0. That means x equals to 1, y equals to 0. So that means my function z will be x square plus y square will be 1 square plus 0 square. So z will be 1. So therefore, corresponding to this point 1 comma 0, I will be having a height of z equals to 1. So suppose this is my height, z equals to 1. Okay. So we will be having a concentric circle of radius 1, like this, a level curve like this. And this will be the height, this point, 1. Okay. Now, suppose you have a point 3 by 4. Okay. So when x is 3 by 4, you can see where y has to be 1 by 4. So suppose you have something like this. So we have 3 by 4, comma 1 by 4 lying on this line. Now let us see what is the corresponding level curve which it is going to touch. So we have z equals to x square plus y square. So that is going to be 3 by 4 square plus 1 by 4 square, which is going to be 10 by 16. So I am going to have a height of 10 by 16. Okay. So 10 by 16 is nothing but 5 by 8, which is, more than half. We can see that. Okay. So suppose this is half. So more than half, suppose somewhere over here. So I'll be getting again a level curve. Okay. And suppose it is going to touch like this. So, my graph is running like this. This constraint x plus y equals to 1 is giving me a curve on this surface, on this 3D surface. Okay. Now, suppose I put x equals to half. So when x equals to half, y is also equals to half, half comma half. Okay. So now what is happening? Z will be equal to 1 by 2 square plus 1 by 2 square, which is going to be half. So suppose this is my half. So again, I will be having a level curve, z equals to half like this, x square plus y square equals to half. And then it is going to touch this like this. Okay. So what is happening? We are continuing like this. Now suppose I take x equals to 1 by 4, then y will be 3 by 4. So 1 by 4 comma 3 by 4. So z will be 1 by 2 square plus 3 by 4 square, which is going to be again 10 by 16, which is going to be again 5 by 8. That means I'm going to turn now. You see that? So how is my constraint behaving on this surface? I am making a curve like this. So I'm decreasing, 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 coming here, and I'm taking a turn, and this process is going to continue. Okay. So just see what has actually happened is this. If we look at 2D, there was a circle of radius 1 initially. Then again, the radius decreases. And then it kept on decreasing. So here I had a level curve corresponding to x equals to half, y equals to half. So what was happening? The curves, it was crossing level curves like this, level curves like this. And then it is actually taking a turn back. Okay. So you note that the value of z equals to x square plus y square is becoming least when x equals to half, y equals to half. So what is happening at this particular point? Suppose this point is C. At this particular point, the graph is taking a turn. So what is actually happening? The level curve and the constraint equation are tangential to each other. Okay. They are becoming tangential to each other. They are touching each other. They are not crossing each other. So what is happening? So my level curve. So what was my level curve? My level curve was z equals to f of xy. and level curve is becoming some constant because I'm giving constant value. So I have a particular level curve fxy equals to c1 is tangential to the constraint gxy equals to c. That is what has happened. So whenever two curves are tangential to each other, so basically what is happening, the slope of tangents at the point of contact become equal. Okay. So now what does it mean? It means f dash of xy, okay, d by dx, okay, that should be equal to g dash of xy at the point of contact. So basically we are talking about dy by dx and we have functions of two variables over here. So when I differentiate f with respect to y, okay, what is going to happen with respect to x, because we are differentiating with respect to x. So first we will differentiate f with respect to x, okay, dx by dx plus then fy dy by dx. This is equal to, because now you can see that this, suppose we are talking about this derivative. Now note that what is happening is that d by dx of f at xy should be equal to d by dx of gxy. Okay. So now we already know that f of xy equals to c1, which is a constant. So if we differentiate both sides with respect to x, what is happening is this. This is equal to 0. So f of x y, this is becoming 1 plus fy xy dy by dx is equal to 0. So from here, the slope, the dy by dx of our given function is coming out to be minus fx divided by fy of xy. Fx is the partial derivative of f with respect to x and fy is the partial derivative of y with respect to x. This is happening for my function fxy. Okay. Similarly, if we talk about this, we differentiate both sides with respect to x. We'll have the partial derivative with respect to x, dx by dx, plus gy xy dy by dx equals to 0. So from this side, the dy by dx is coming out to be minus gx xy divided by gy of xy. This is known as the necessary condition for finding the optimum value of a two variable function with respect to a constraint, an equality constraint. So what has happened is that now we will equate both these derivatives. So what is the condition that we have got? The condition that we have got is minus fx x comma y divided by fy x comma y should be equal to minus gx x comma y divided by gy x comma y. Okay. So basically, this is our necessary condition for optimal value. Now, in the example which we had taken, we could see that our fxy was x square plus y square and our gxy was equals to x plus y. Okay. So if we put the first derivative, that is going to be 2x by 2y equals to 1 by 1. So that would imply that x equals to y. And we know that x plus y was equal to 1. So x plus x was equal to 1. So 2x equals to 1. So x equals to half. So here the optimal value. Now optimal value here means the minimum value exists at x equals to half. And we have already seen that via this diagram, what was actually happening. The curve was behaving like this. Corresponding to each point on this line x plus y equals to 1, there was a particular z value on this surface. For that particular z value, we drew a curve, we drew a level curve, we plotted a point on that level curve. Now, for different points on different level curves, we draw a graph, and then we saw that the graph was reaching a minima at the point C where the value of x was half. Okay. Now notice that z equals to x square plus y square is greater than or equal to 0 because it is the sum of squares. and it keeps on increasing. Okay, so if over here we consider the minimum value only, we get the minimum value via the method of level curves. So this is a necessary condition to find out the optimum value of a function of two variable subject to a constraint, and that constraint lies on xy plane in 2D.